Let's take in a random population, real coded genetic algorithm. And let me write down random numbers for some of them at least. So on. And let me write down random fitness values for each one of them. Okay, now what I need to do is I need to select some individuals so that I can do reproduction in them. So I have to select some individuals so that I can do some reproduction to them, or I need to apply the selection operator. So this is currently my individual, and this is what is currently my, I cannot use the word fitness technically because it's a cost. For the minimization problem, I would have used the cost, which it is. For the maximization problem, I'll use fitness, but informally fitness, even though I know this needs to be minimized, I call the word fitness. Now, suppose I need to select 4 individuals. Suppose I need to select in 4 individuals. And for some time being, let us assume the individuals which do not get selected, they'll eventually die off. So in order to do this, I'll apply a selection operator. So I need to select 4 individuals in general, k individuals from a population size of n. And the most obvious thing that you could think about is probably that let's select the best 4 individuals. So that's number 1, 0.12. The next is 0.35. So that's rank 1. That's the best. This is rank 2. Remember, it's a minimization problem. The next best. And the other 2 are rank 3. And the last one is a rank 4. That's intuitively the best thing that you can think of. This is what's called as a top selection strategy. And it's a valid selection strategy. However, let me tell you that now with everything there will be pros and the cons. So it's extremely simple. You just sort all the individuals and select the k top of them, in this case 4. So it's absolutely inherently extremely simple strategy, which is something that works wonders for me. But let's discuss the problem as well. Now, in real life, what happens is that sometimes an individual who looks extremely bad turns out to be a great individual in the future, and therefore you have to be more considerate about them. So a few years ago, people who were saving would have been bad people. Why save? There was a lot of liquidity in the market was booming. But then, of course, now it turns out that those individuals who earlier were made fun of for saving are actually good because many people lost their jobs during the pandemic, unfortunately, and the savings of those people helped. So suddenly people realized those were great people. So had we completely ridiculed them, had we completely convinced that nobody saves, it's bad, had we killed all those individuals who were saving, had we made savings illegal because momentarily it appeared to be something extremely bad, then there would have been a great chaos, especially in India where there is limited social security. So it was something which was absolutely good. From sea, when someone would have said, I want to go to land, people would have said, why do you want to go there? There's absolutely nothing over there. The world is at the sea. And then if people would have ridiculed that person, said there's nothing good in that, said that it's absolutely crazy, there's direct sun, there's no water, blah blah blah. So we wouldn't have got all these interesting life forms which are on land. Some years down the line, when people would have started working on twos instead of fours, they would have been made fun of. It's non-intuitive, it doesn't solve any problem. Now those are great people because now we understand the advantages of working on twos. So when you do something new, initially you may be ridiculed, you may be extremely unfit, you may be out of the box for no reasons, you may be unfit, but then you are still important because characteristics which immediately appear to be extremely bad may later turn out to be extremely good. And that's exactly the situation over here. This individual may have a gene which may currently appear to be extremely bad, but later may turn out to be very good. So let's not kill it. Let's not kill it. But then that means that I cannot kill this one, 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 I cannot kill anybody. So everybody survives. And because everybody survives, therefore, my entire theory of evolution and younger generation being better than the old previous ones is into the dustbin, because everybody survives no matter how good or how bad you are. Nobody dies off any time. And what I've done is that I have contradicted my own statement. Earlier I said that in evolution the fitter survive and the weaker die off, and that's why the population keeps on getting better and better. There's incentive to learn something new because only then you survive. So you have to fight for your survival, and therefore there's a constant urge, a constant fire in people to get abreast with the latest changes in the environment or get fitter than their parents, otherwise they'll die off. It's a ruthless real world. If you cannot run, you get attacked, you get killed. If you cannot survive the heat, you die off. So you need to learn good characteristics, and that was only because the weaker ones were getting killed. Now I say nobody gets killed, so because they may have some interesting characteristics, and therefore the old theory does not hold good, it's contradicted, and that's dangerous because there'll be no incentive of developing new characteristics. Everybody survives, so nobody will develop new interesting characteristics. And therefore I say that there are two strategies which are possible. So I say strategy 1, only fit survive. And strategy 2, I say weak also survive. And let's analyze both of them up. So if only weak survive, the clause is that weak individuals may have characteristics useful for future, and the con is over here, if only fit survive, that weak individuals die who may hold useful, so I'm writing the same thing again, future characteristics. It's the same line, so the plus of one is the con of the other one. And I've got another interesting thing. So the plus of this thing here is that if only the fit survive, I say new population better than old, because of course the weaker individuals die, and therefore on the whole the population is better, and the better mutations that you do, are rewarded by survival, and the worse mutations die off. So new population is better than the old, and that's exactly the con of the old one, that new population may not be better than old. Because everybody's surviving. Now, whenever I am contradictory pros and cons, what I'll do is I'll stochastically select strategy 1 and strategy 2. That's what we always do in every algorithm. If this has pros and cons, if this has pros and cons, we stochastically select some from this, some from that. So my resultant strategy is stochastically choose from strategy 1 and strategy 2, and it's obvious that giving more emphasis to strategy 1, because strategy 1 is the normal evolution, the fitter survive, the new population is better than old, new better mutations are rewarded by survival, they are encouraged by more reproduction. So if fitter individuals will not reproduce and produce more children, you won't get a lot of better individuals in the newer population. That's actually weird with the human population. The smartest people don't reproduce more children, but then the human population is not driven by the same rules which were laid by Mother Nature. So giving more emphasis to strategy 1, because the new individuals need to be better than the old one. The fitter individuals should reproduce more, they should produce more children so that the newer population is better, and the weaker individuals are bad for the animal, they are bad for the society, so they should die off. And now my top strategy is only strategy 1, so I'll add some characteristics of strategy 2, and the new strategy will be called as roulette wheel strategy. So let's convert the fitness value into a term called as a probability of survival. So this individual should have high probability of survival. So let me randomly do it. I'll formalize this up a little bit later. So let's say it's 0.3, and this individual, which is the last, should have nearly 0 probability of survival. So the next high is this individual, which should have a slightly lower probability of survival, and then it's rank 3, and then it's rank 4, and then it's the last rank. So that's my probability of survival. So I'll formalize this up in a minute. So what I do is I take a roulette wheel, which is the same wheel that you get in fun fairs. It has one pointer, and the individuals are over here. So let's draw the individual. So let's say this is individual 1 with a 0.3 of circumference. So that's individual with rank 1. So let's name the individuals as x1, x2, x3, x4, and x5. So this one is x2. x1 is with a 0.2. I should have started with x2, so let's correct it. So that's 0.3. x3 is over here. And x4 is over here with a point. So x3 is 0.25, and then you have x4 0.19, and a very small x5, which is actually pretty bad. So I roll this roulette wheel, and an individual comes out as a result of it, and the individual that comes out is the one that will be selected. So programmatically you actually have, that's just to show it as a figure, so that's a roulette wheel. So you have x1, x2, x3, x4 and x5 with 0.2, 0.3, so what you say that I take a new access system starting from 0 here that goes all the way up to 1 here. So 0 to 0.2 is the first individual, 0.2 to 0.3 plus 2, which is 5. So 0 to 0.2 is 1 till 0.5 is the second individual. From 0.5 to 0.75 is the next individual. From 0.75 to 0.94 is the next, and 0.94 to 1 is the last individual. So I select a random number from 0 to 1. So that's a random number from 0 to 1. So let's say r is equal to whatever, 0.8. And then I do a binary search over these numbers, 0, 0.2, 0.5, 0.75, 0.94. So 0.8 turns out to be here, which means x4 is the one that's going to be selected. Even here you can see that my wheel is rotating, so it goes at 0.8. So that's 0.5, that's 0.75, and this one is 0.8. So that's x4 which will be selected. So it's a binary search. I do it 4 times. So let's say if I do it 4 times, the individual selected first was x4, then x1, then x2, and then x1. So 4 individuals get selected. The chances of fitter individual get selecting are high. The chances of weaker individuals getting selected are low. And that is what is a roulette wheel selection. So it trades off between strategy 1 and strategy 2. So the fitter individuals are selected multiple times. There is large chance, and the weaker individuals are with some probability selected. Like x4 wasn't really fit, but it's still selected. So there's a chance that weaker individuals also get selected. It's trading off between strategy 1, strategy 2. x1 is extremely good, and because x1 is extremely good, it gets more ladies, it gets more mates, it gets more people interested, and because of that it makes more children. And because x1 is good, its children will also be good, not for the human generation because it is now less genetical and it's more to do what you do with your life. We've reached that stage of development genetically. So physically we are all healthy, and mentally it only depends on what you do. So x1 was good, and therefore it produces more offsprings. But x4, even though it was bad, it gets selected. The problem is x2 was actually good, and it gets selected 1. x3 was reasonably good, it did not get selected, which is okay. So in order to accommodate a bad x4, somebody needs to sacrifice, so it was x3. So it's doing what it wants. That's a roulette wheel selection. Now again, let's see if all the problems have been solved or there are problems which are unsolved.